Hi everyone, I am Farad Nawaz from the University of Illinois. I will be talking about our paper on explorative probabilistic planning with unknown target locations. First, I would like to take analogy from the game of battleships. So the game goes like this. There are a set of ships placed on a board, and the objective is to hit these ships as quickly as possible. And the glitch is, you don't know the location of these ships, but you have some prior knowledge on how these ships are placed. For example, in this scenario, the ships are placed either horizontally or vertically. Let us look at a typical game playing scenario. You try hitting this cell and you haven't found the ship. So you try few more cells and you finally hit successfully. So you try the nearby cell and you found one ship. Now the game goes on. This is a successful hit and you found another ship and eventually you found all the ships. Some hits are successful, some are not successful. And now let's describe how we actually played this game. First, you tried hitting few cells, and if a hit is successful, then you tried the nearby cells. Now, this is somewhat similar to a robotic path planning scenario. Consider a Mars rover where the objective is to collect water samples from Mars. Again, the glitch is you don't know exactly where these water samples are located, but you might have some prior knowledge from the maps obtained using the orbiters revolving around Mars. They give you an idea on where these water samples are located. So the problem which we would like to address is how to optimally explore target locations. In this case, the locations of the water samples are the targets while completing the mission in minimal time. First, I would like to start off with some mathematical preliminaries. I want to describe how the agent interacts with the environment, and this is given by the transition system. For example, a 4 by 4 grid world here is an example of a transition system. The cells are the states. The transitions are to go either north, south, east, or west, and each state has a label. The label of this state is an obstacle. This is target 1 and this is target 2. All others are vacant. And each state also has some neighbors to it. Now, how to describe the mission specification? It's given by a linear temporal logic. Let's say the mission is to eventually visit the targets while avoiding the obstacles. It's given by the formula phi, which describes eventually visit T1 and eventually visit T2 and never visit the obstacle. Obviously, the goal is to satisfy this formula phi. Now, to track the satisfaction of the specification, you have an automaton graph. Each state of this graph describes a possible history of visited labels, and the transition depends on the label of the subsequent state in the transition system. And your goal is to get to the final state Q3, which satisfies the LTL formula. Now we describe our problem. So the problem is given by this LTL formula phi. So each specification I inside this complete formula is a reach wide problem. So you have to eventually visit a set of target states and never visit obstacles. Now look at this. You have these I specifications which are connected by logical OR operators. So it is okay for you to satisfy at least one of the n specifications, but you have to do it in minimal time. The motivation is obvious. You have to visit a set of target states while avoiding the obstacles. And we consider these assumptions for our problem. The states and transitions are known. The agent knows the labels but does not know the mapping from the states to the labels. The agent also knows its state and the labels of its state and its neighbors at every time t. Now we consider the motion of the agent both in the transition system tau and the automaton A, hence we consider the product system. Let us come back to our running example. Let us say that the agent starts from this initial state. It goes here. Since there is no change in the history of visited labels, the agent stays in the same state in the automaton graph. Now it goes to T2 and hence it goes to Q2 in the automaton, and it goes to T1 and eventually it visits the final state in the automaton, satisfying the LTL formula phi. Now let us consider another path. It starts from the same initial state. It goes to this state here and there is no change in the history of visited labels, so it stays in Q0 in the automaton and hits the obstacle in tau. And there is no way the agent can satisfy the LTL formula 5, so the agent is dead right now. We use this terminology interchangeably. A transition system is equivalent to a directed graph with labels. The prior knowledge is described by a probability distribution P of the possible labeling functions. Let us say that the prior knowledge we have is that the pairwise Euclidean distance between the targets and obstacles is always less than 2 units. So in our running example, these are two possible labeling functions of our transition system. There are many other labeling functions as well, which is not shown here. The agent also has some local sensor information, that is, it can see the labels of its state and its neighbors. So consider the agent starts from here. The white cells are known to be vacant, and the black cells are those states whose labels are not known. Now, as the agent moves, it discovers more information. It has also discovered that this state is an obstacle. We can see that the transitions in the product system are uncertain. This is because the transitions in the product system depend on the labels of the states. And we don't know exactly the labeling function of the states in the transition system. It is given by some probability distribution P. Therefore, the existence of an edge in the product system is probabilistic. Now, this Canadian traveler problem is exactly what we are tackling here. The problem is to optimally visit a network of cities with unknown road blockages. This is a road closure map of a city in Canada. The strategy to tackle this kind of problem is to optimally explore and exploit the environment simultaneously. So, as you move on the environment, you discover more about the existence of edges on the map, and that leads you to explore the environment. And you also need to exploit because your eventual goal is to satisfy the mission specification, and each edge might take you closer to the mission or farther away from the mission. The first procedure in our solution is to create a model graph G bar. So G bar is exactly the product transition system with the same states and edges, but the edge might be in the graph or not with some probability P. And you assign weights to these edges, which provides a metric of optimality. One edge is for exploration. So lower the exploration weight, better it is for the agent to explore the environment. So the idea is you go to a vertex with a large number of uncertain edges. So once the agent goes to the vertex, it can discover more about the edges which are uncertain. And the second weight is the exploitation weight. So your goal is to visit a certain number of targets while avoiding the obstacles. So you give a large exploitation weight if that edge takes you possibly to more obstacles, and you give a small exploitation weight if the edge takes you towards a target. I describe a complete path planning algorithm. First is to initialize the automaton A for a given LTL formula and construct the model graph G bar. Now you search for a shortest path on G bar to a final vertex, and you traverse this shortest path. So as you traverse, you update your possible number of edge configurations, and your model graph G bar might also change. And you traverse the path until your model graph G bar changes or till the end of path. And you again compute the shortest path on this new model graph, and you repeat the procedure until your specification phi is satisfied. Let us consider a numerical example where we implemented our algorithm. So this is a true environment which is a priori unknown to the agent, and you are given some mission specification which the agent has to satisfy in minimal time. So in simple words, the mission is to visit a set of targets while avoiding the obstacles. To be more precise, you have to visit all the three targets if the agent hits an obstacle. And if the agent doesn't hit any obstacle, then it is okay for it to visit at least one green target and then one blue target. And you also have some prior knowledge. So the prior knowledge which we used in this example is these four obstacles always lie on the four corners of a 4x4 grid, and the three targets always lie inside the square or along the sides of the square. The pairwise distance between these targets is always at least 2 units. And from this prior knowledge, we compute these probability distributions, which give you the probability that each of our target's obstacles lie in any of these cells. And this is a simulation video of implementing our algorithm. The agent starts from here, and as it moves, it discovers more about the environment. The black cells are still unknown. It has discovered obstacles. It has discovered a target. It hits a target. It has discovered another target and it hits a target. And the specification is satisfied, and our procedure completes the specification in 10 steps. We compare this to the Westphal's algorithm, which is a popular algorithm to solve the Canadian traveler problem, and it requires 20 steps to complete the same LTO specification. The conclusion is we have utilized linear temporal logic and automaton theory to satisfy machine specifications, and we proved that the problem we are tackling is exactly a Canadian traveler problem. And the solution we proposed is to simultaneously explore the environment and exploit the machine specification. From here, the path forward is to provide some theoretical guarantees on the optimality of our proposed solution and how long does it take to complete our algorithm to satisfy the mission. And we also are looking forward to automate the conversion for a larger class of LTO specifications. For here, we now consider only reach-wide problems, but we are looking to convert from some form of structured English to a product system directly. Uh, that's it for today. Thank you for listening. If you have any questions, please let me know. And if you want to talk more about it, you can contact us at these email IDs. Thank you.